Okay, my last I'll dwell on a little bit more here is one of my favorite objects, Eta Carinae here, where they did some very high resolution studies of this particular object, and I'll say a little bit more in detail of what it is. Got some. I'll get back to this map here later. But most of this data was taken, and it's the highest resolution data set ever taken of this Eta Carinae star system. And it was taken by the VLT, which is the telescope facility, the Very Large Telescope Facility run by the Europeans down in South America. And I'm going to let you listen to the trailer that they have for this facility, which I think is pretty cool. And I'll point out a few things that are in here. It's not very high. It's only about 9,000 feet or so. Driest place on Earth. There are places that haven't seen rain for a couple hundred years in this part of South America. These are the telescopes I'll be talking about a little bit more. These are these outrigger telescopes. They're 1.8 meter telescopes. These are the big guys who are 8.2 meters in size. You can see a car here. You see the size of that. I've done other reports on instruments that have gone on these particular telescopes, and their instrumentation is indeed incredible. These are the auxiliary telescopes that I will talk a little bit about here that took the high resolution images that we'll see, look at, or some of them. I'll get into that part as well. One in the infrared and one in the visible part of the spectrum, the VST and the Vista telescope, like V and everything. Now, I've never been to South America myself, but I'd like to go to this facility when I have a chance. I do have one of the instruments that I build that's down there on one of the sites, not this particular one, that I need to go visit one of these days. The adaptive laser guide stars produce laser point into space basically and illuminate a sodium layer up in the higher atmosphere to produce an artificial star, which then produces a guide star that allows you to get better resolution correct for the atmosphere there. Here's one reason to go down there. They've got a very nice facility, but that's down there. But I see no astronomers sitting in the benches over here enjoying the pool. Yeah, much of the report here in 60 minutes or observations that we've done by the ESO facility. Is it not cool? Okay. I will talk closer to the mic here. Looking at black holes in the center of our own galaxy, we have about a 4 million solar mass at the center of our Milky Way galaxy. That's also being done from Mauna Kea as well. Andrea Getz, if you've seen our black hole show, is working on the same, tracking those stars that are in the center. I would agree with that statement. Okay, so let's look at Eta Carinae. Here's some pretty pictures zooming in on the Eta Carinae nebula. This is actually done by this image is from the VST at that VLT site. there. Eta Carinae is this star right in here, kind of washed out, and I'll show a couple other ones. Again, you can see it over here in this direction there, and in a closer view, not taken at this site here. And even closer, there it is right there, and this is, I believe, an infrared image here, where you can see some dust and such. Okay, here is one of the images that they released utilizing one of the bigger 8.2 meter telescopes in the infrared part of the spectrum. And in the infrared, you can actually use the adaptive optics that was shown in the movie there, where you get higher and higher resolution. This is Eta Carinae buried down inside here, which is a pair of stars thought to be, the primary star thought to be about 90 to a couple hundred times the mass of the sun. The secondary one that are orbiting around it is still no dwarf at 30 solar masses or so. And this nebula is actually called the Homunculus, which is a great name for it. And many of you have seen the Hubble images of that, which is this one here, which is also an outstanding image there. But the other one is the best that we've ever gotten in the near infrared from the ground. This is a visible image, and Hubble also did some deeper images of this area. My mic seems to be breaking out a little bit. Am I holding it too close?
Not close enough.
No, not close enough.
It seems like it breaks out more when I hold it close, but I'll try. So you could see some of the outlying areas of this homunculus area. That nebula was due to an eruption of this star back in about 1850. And so this is looking at the magnitude of the star that dates go all the way back to 1686. Here are a few points of that star. And it was at this time that it brightened to about minus 1 magnitude, which made it actually the second brightest star in the sky at that particular time. Now, you can only see this one from the southern hemisphere, and then it just dropped off where it came down to about 7th magnitude, which is actually below naked eye visibility there. So a huge difference in brightness. Thought that this might have been actually a supernova that had went off, but it turns out it was an imposter, and it just was a giant eruption, and we have now been monitoring all the way up until the current day, and you can see it's brightening again here in the visible part of the spectrum. Now, we don't know what it's going to do ultimately over here. The eruption was a very interesting event based on the homunculus. It actually shed about 30 solar masses of material that went out into that nebula that you see around that from that explosion. That, the image I just showed you, the homunculus, was done with the VLT. The highest resolution was trying to look down and see those two stars that are actually interior to that, and they're getting closer and closer to that. And here is the telescopes, those 1.8 meter telescopes that were used. You can see the Carinae Nebula over here, so it's in this area. There's a great image there of that in the background. And what they do is they utilize 3 of these telescopes, and they can move them around in tracks and things like that. But when you do this here and look at the data that comes from it, it simulates a telescope that is much larger in terms of the resolution that it gets. So they're like radio telescopes, which I've talked about before, where you can collect all the data from the different radio dishes and put them together. The hard part, though, is unlike the radio part of the spectrum, where you can actually record the signals and then use a correlator and computers and things like that to recombine those signals. You cannot do that in the visible part of the spectrum because the frequencies are too high, and therefore have to combine the actual light coming from each of those telescopes. So these are actually the fiber cables that are bringing in the light. There's mirrors that are directing it around. I can't tell you all where all the light is going. There's some dichroic mirrors that are over here that actually split the light into different parts of the spectrum, because it's also, in addition to doing high resolution work, is actually taking spectrum of those objects. It's incredible technology to be able to bring all of this light together and get images of these really small regions. And so it doesn't look like much, but this is the high resolution, and I'll show you some other images how deep this is down into the homunculus nebula. But here is the image. There is the primary star. I don't think you can see the secondary star, but these are the stellar winds that are coming from this. And I'm going to show you a video that was released last year about this time, where they're modeling these stars that are going on there in this region here. So this will show you what's going down deep in there and why we really want to look in this region.
Eta Carinae is the most massive star within 10,000 light years. In the mid-19th century, a tremendous eruption hurled enough gas into space to make at least 10 copies of the Sun, creating an expanding nebula still visible today. New results from NASA satellites, ground-based telescopes, and theoretical models are providing astronomers with an improved understanding of the system. At the nebula's heart lie two giant stars. The smaller of the two is 30 times the mass of the Sun and 1,000,000 times brighter. The primary weighs 90 suns and shines 5 times brighter than its companion. Both stars produce powerful outflows called stellar winds, but the primary's is so dense it prevents astronomers from directly observing the star. The secondary's orbit is among the most eccentric known. Every 5.5 years, when the two stars swing toward closest approach, or periastron, they come about as close to each other as Mars is from the Sun. Eta Carinae's most recent periastron occurred in August 2014, and many of NASA's space-based telescopes, as well as ground-based observatories, looked on. Where the stellar winds collide, temperatures reach hundreds of millions of degrees, hot enough to emit X-rays. But the X-ray emission shuts down near periastron when the smaller star is swallowed up by the dense wind of its larger companion. The X-rays gradually recover after periastron, but they do so a bit differently each time, suggesting structural changes in the dueling winds. Recent observations have helped theorists refine computer models of this interaction. Here, darker colors indicate lower gas densities around the stars, while the stars themselves appear as black circles. When the stars are far apart, the winds collide head-on, creating a huge cavity surrounded by 50 million degree gas. But near periastron, the secondary whips around the larger star, carving a tunnel through the primary's dense wind. The secondary star's rapid motion changes the collision zone from head to tail. The smaller star's faster wind flows out along the cavity it created and then crashes into the outward-moving wind of its companion. From our perspective on Earth, the X-rays fade, then recover as the stars move apart. New 3D models of these simulations reveal the formation of finger-like protrusions along the cavity near periastron, features never before identified. Theorists now investigating the phenomenon suggest they may arise from instabilities developing in gas as it flows along the cavity wall. Astronomers also keep an eye on Eta Carinae with the Hubble Space Telescope. These images show a structure resembling a crab, formed by gas excited by the secondary star's intense UV light. This light dims near periastron when the secondary passes through the thickest part of the primary's wind. The gas relaxes, settling into a lower energy state. As a result, the crab appears in a different spectral line until the stars move apart and the UV light is restored. Eta Carinae is one of the closest and most massive colliding wind binaries and serves as a natural laboratory for studying these rare and important objects. While its past eruptions remain unexplained, astronomers think they have a handle on its current state, a claim to be tested at the next periastron in February 2020.
So you can see why we want to get some higher resolution capabilities to look down into this amazing object here. They quoted lower masses than they're quoting today, so that the larger one is maybe 90 at the minimum. They think it might be as much as a few hundred solar masses, as well as the secondary. And looking in closer, you can also identify their orbits a little bit better, so that you can get those distances, so that you can actually get a better handle on the masses. So it can be a very interesting object to study. So here again, here's the background of the Carinae Nebula. You can see the blow up of where they're looking. So here is the homunculus, and you can see that tiny little square. That is that region that they have blown up, and you are seeing those winds coming from that star. So anyway, stay tuned on this object. So they're getting these capabilities to really study it better in that 2020 time frame. And so it is a very interesting star. You can see that it's brightening up in this location, and it is an object really like no other. I mean, in the earlier 60 Minutes this year, I reported, I think it was the January of last year as well, where we try to look for Eta Carinae-like stars in other galaxies, and we have found a few, but they are very, very rare. They're really high mass, and so here it represents the evolution of stars. There's kind of a dividing point here between low mass and high mass stars. These higher ones becoming supernova, either producing black holes or neutron stars at their core when they're done. We don't know a lot about these supermassive ones, which were Eta Carinae is in. And it's also involved in this binary system where it's obviously losing a lot of material in this interaction and these interruptions. We do not think it will lose so much mass that it won't form a black hole. So it will definitely form a black hole and form a supernova. There are some other objects that we have found that had similar kind of events where they've had what looked like a supernova and turned out to be an imposter, and then later blow up in a supernova. So this object may be one of those ones that's going to blow up soon. We don't know. It's classified, the primary, as a luminous blue variable star, where previously we didn't think they would go supernova in that stage, but 1987A, the supernova in Large Magellanic Cloud, was actually one of those types that blew up in a supernova. So it's unclear as to how things evolve in this stage here. And when it does go supernova, what it's doing is basically it's running out of fuel at its core. It's forming an iron core in there, and when it runs out, there's no more energy to be attained in the center of the star, and it implodes, which ultimately forms the black hole at the core. But depending on the dynamics of its interaction, these outer layers, whether there's fuel left in it at all, depends on how bright that supernova may or may not be. And there are different types of supernovas. There's one of these called hypernovas. They're even brighter than your traditional supernova. If this is a regular supernova at its distance at 7,500 light years, it will reach the brightness of Venus. About a -4 magnitude when it goes supernova. If it's one of these hypernovas, it'd be even a factor of 5 to 10 brighter than that. So it'll be an incredible object. Hopefully it goes soon so we can see what's going on in that object. So a lot of details, though, that we don't know about, but they're very, very interesting objects. We don't have a lot of anything to compare to in these objects. So this is something that astronomers will be studying for a long time, including after it blows up, whenever that might be, between now and 100,000 years or whatever. Okay, I'm going to leave you with one last little video here, which the ESO always produces nice little zooms to give you an indication how big a space that is. So we're moving into from the Milky Way down into the Carinae Nebula, just to show you how small of a space or point on the sky or area on the sky that we're actually looking at. I love the way they bring in different images to represent these zooms. That's the Hubble image that you're seeing there. And then there's their image from VLT. That is the little star that's in the center of all that madness. All right. Thank you very much, and I'll turn it over to Steve.